Welcome back everyone to the second part of the Unsteady panel method lecture. And to remind you where we left off last time we left off at the place vortex step where we place a newly shed vortex after the trailing edge, which is representative of the shed vorticity at the trailing edge of the wing. So the fifth step here is building the A matrix, which is reminiscent of the A matrix that we built last time when we solved for the steady case, but with some main differences. So let me write that down. In this step, we construct the A matrix. So, and as I said, this is mostly similar to steady case, or the A matrix that we found in the steady case, except for two things. The first thing is that in this unsteady scenario, we have to enforce Kelvin's circulation theorem, which again means that d gamma dt of the entire system for all time is equal to 0. So if we start off with 0 circulation, the entire system has to always have 0 circulation throughout time. And the second thing is that we have to find the gamma of newly shed vortex. So in contrast with the steady scenario where you only find the gamma of the bound vortices, here you find the gamma of the bound vortices as well as the newly shed vortex. So before we start actually describing the A matrix, let's go over Kelvin's circulation theorem really quickly here. So this is the system we're looking at. Assuming that the system has started from rest, so the wing is starting from rest. For a wing starting from rest, there is no circulation because the fluid is empty of vorticity and there is no bound circulation in the wing. Once the wing starts moving, then it will start building some bound circulation, and thus it will need to shed some vorticity such that the circulation of the entire system stays at 0. So to write it down here, if gamma at t equal to 0 is equal to 0, and via Kelvin's circulation theorem, we know that d gamma dt of a system for all time has to always stay constant. Thus, the circulation of a system stays constant, and thus the d gamma dt is always equal to 0. Like those two things here imply that gamma for all time of the entire system will equal to 0. So in this scenario, the shed vorticity and the bound vorticity should cancel out. So how do we formulate this in equation form? Let's say we have NV bound vortices shown here. We can say, or we can try to sum the circulation. So gamma 1 corresponding to the first bound vortex plus gamma 2 corresponding to the second bound vortex, so on and so forth, until gamma NV, which is the last bound vortex. Now we also have the additional unknown vortex here, which is called gamma nu in this case. So let's put gamma nu, and this is the vortex strength of the newly shed vortex in the proximity of the trailing edge. So all these gammas are unknown and we have to solve for them. So all of this we know is equal to the shed wake. Well, we know that the circulation of the shed wake here is gamma of wake of t minus delta t, which means that at t, this is the wake. But in the earlier time step, before we shed this vortex, this was the wake. So we were missing this vortex. So essentially, this is a statement saying that the circulation sum of this bit here, which is that, plus the new shed vortex in this time step, plus the wake in the previous time step, or the circulation of the wake in the previous time step, all that should sum to 0. So we can move this to the other side, and that would give us gamma 1 plus gamma 2 plus gamma NV plus gamma nu is equal to minus gamma of the wake at the previous time step. So again, to reiterate, the gamma, or the circulation of the wake at this time step, involves or includes this gamma, the gamma of the newly shed vortex. But the circulation of the previous time step is this wake, entire wake, minus the newly shed vortex. All right, moving on, we can form the matrix. So we start off exactly as we did last time, right? Remember the influence coefficients. We have A1, 1, A1, 2, A1, 3, where the first index is the collocation point, and the second index is the bound vortex. So it goes until A1 and V, and then we go down. So now we're varying the collocation point when we switch from one row to the next. So we can just populate this matrix simply, A2 and V, and again we go down until the last collocation point, which is A and C1, A and C2, well, 2, A and C3, up until A and C and V, which is the influence coefficient on the last collocation point due to the last vortex, last bound vortex. Well, we also, not to forget, we have an additional bound vortex. Sorry, not an additional bound vortex. We have an additional unknown vortex, which is the newly shed vortex. So we have an extra set of influence coefficients, which are related to the effect on the collocation points, or each collocation point due to that new vortex. And then we'll just call this A1 new to indicate the new vortex. So A2 new, and then A and C new, which is the influence coefficient, the influence coefficient on the last collocation point due to the new vortex. All right, great. So we have set this influence matrix, and then we have an unknown vector which corresponds to the unknown gammas, gamma 1, gamma 2, up until gamma NV. And then we also have the new vortex, so gamma nu, right here. Which is equal to, again, right-hand side. And then we will go over forming the right-hand side in the next step. But for now, let's call it right-hand side, RHS1, RHS2, and go down to RHS and C. These right-hand sides are simply the velocities induced at each collocation point due to the flow, free stream, as well as the shed wake right here. So we are missing an additional thing, which is enforcing Kelvin's circulation theorem, where, I mean, we found this equation here, right, which is an equation that enforces Kelvin's circulation, saying that the circulation through time will be always constant. So all we need to do is translate this equation into the matrix here. And this is done by simply inserting this equation into the last row, which I'm going to do here. So as we said, well, we know that gamma 1 plus gamma 2 up to gamma NV, which would correspond to putting ones all across this matrix. So this row multiplied by this column will give you this right here, correct? So this bit here is equal to the circulation of the wake in the previous time step. So it's minus gamma W of T minus delta T. Moving on to step 6, we build the right-hand side vector, which is this vector right here. Let me change color. All right. Recall that RHS sets the no flow through or no penetration boundary condition. And here we apply at collocation points in wing fixed frame. For some reason it just cut out, so let me move to a new line in wing fixed frame. So it's pretty much like the setup we had last in the steady lecture. We find the velocities induced at the collocation points due to the kinematics, as well as the wake in the case of unsteady flow. And we find those at the collocation points in the wing fixed frame. So just like we did in the steady situation. Okay. Velocity contributions on each collocation point we have two sources of velocities at the collocation points. In this case, kinematics of the wing. So we have velocities u and w, which are the velocities in the x and z axes of the wing. So let's assume that you have some sort of cambered wing right here, and this is the chord. As we have said before, this is the x and small z, so u is in this direction and w is in this direction. Okay, the first component is the components due to the kinematics, which can be obtained here. Or sorry, not kinematics, I meant the component from the velocity of the wing, so the horizontal and vertical velocities of the wing. Here we can find this component in the wing fixed frame using the rotation matrix that we talked about before. This is the rotation matrix taking you from the inertial to the wing fixed frame of the vector minus x dot naught and minus z dot naught, where x dot naught is positive in the positive x direction, and z dot naught is positive in the positive z direction. Obviously, these are in the inertial frame. We also have an additional component if you have a pitching wing, and that is represented by the following vector: minus alpha dot multiplied by collocation point at I, z, j, and alpha dot collocation I dot x and j. So let me explain this really quickly. Assume that you have this cambered wing pitching about some point, and here we are assuming that the positive alpha is in this direction. So pitching up is a positive change in your angle of attack. In this case, so let me redraw this again to give you an illustration. Assume that you have a wing at 0 angle of attack, and you have a, let's say the pitching point is about some distance from the leading edge. So if your pitching point is here, then you place your wing fixed axis here, x and z. In this scenario, if you are pitching in this direction, that means that this side of the wing is moving up, the side of the wing is moving down, and thus the wing itself sees, if this wing is moving up this way, it sees an opposite velocity profile building up. And if this wing is pitching this way, then this part of the wing is moving down. And since it's moving down, it sees a velocity going up like that. So this is the velocity experienced by points on the wing from the flow in the point of view of the wing itself. And since, assuming that this is sort of some sort of linear rotation, if you are rotating at a pitch rate of alpha dot, then the velocity of this point is alpha dot times this distance here, which is just x. This is the velocity in the vertical direction, right? And we know that this velocity is negative because it's going down, so it's really minus alpha dot x. And we assume, well, my apologies here, it's alpha dot x, and since the x position is on the left side of the origin, then x is negative, so you get a negative velocity. At the same token, if this is at some distance, let's say x prime, then the velocity is alpha dot x prime. And so the velocity is alpha dot x prime is positive, thus this expression is positive, and this checks out because the velocity seen by this point is actually going upward. This is basically what is happening here, but it's a more generalized scenario if you have a cambered wing rather than a flat wing like the one here. So let me write that down. The stuff here is for surge and plunge, and surge basically means motion in the x-axis, and plunge means motion in the vertical or z-axis in the inertial frame. And this bit here is when you have pitching. So if you're not pitching, this bit goes to 0. Obviously, you can also add additional terms depending on the if you have a changing camber or not, but for the sake of simplicity, we'll just keep it at that. And if any of you needs to actually know the additional terms due to changing camber, we can go over this individually. So this is the first component, the kinematics. The second component is due to the wake, or the wake vortices. Now, all wake vortices except newly shed vortex, because remember, that's one of the items we're solving for because we don't know its strength yet, so we don't include it when in the right-hand side term. And like the steady panel method we derived last time, we can use the function use vor2d to determine these velocities in the wing fixed frame. And this is important to keep in mind. Don't mix wing fixed frame and inertial frame here, because that will give you the wrong solution, since we are working on developing the system of equations. We are working here in the wing fixed frame. All right, moving on, and I will give an example on what that looks like. So example here, velocity contribution of wake vortex J. So we are going to single out some vortex J that's in the wake on some random or arbitrary collocation point I. What does that look like? The vector, the horizontal and vertical velocities due to the wake vortex J is expressed here. And remember, this is wing fixed frame is equal to vor2d, the function that we came up with last time in the steady panel method, of the strength of said vortex, the locations of the collocation point in the wing fixed frame, as well as the position of the wake vortex, also in the wing fixed frame. Thus, the velocity contribution at the collocation point I that we're talking about by all the wake vortices. So we find the velocity induced at the collocation point of interest due to the entire wake, except for the newly shed vortex, because we don't know the strength of it yet. That could be given by simply the sum of the separate components regarding each vortex. So that is represented here. So we do this step for all the vortices at the same collocation point, and we just sum them. And now we do this at each collocation point. And after you do that, we can find finally the right-hand side. So for collocation point I, the right-hand side is equal to minus the influence of the kinematics plus the influence of the wake in both directions, the vertical and horizontal, and again in the wing fixed frame, Now dot it with the normal unit vector at that collocation point. So, and again, this normal unit vector is, I need to make this clear, so I'm going to use another color. This normal unit vector, since we're working in the wing fixed frame, this is in the wing fixed frame. And this simply takes the induced velocity component that is normal to the collocation point surface of interest. And then finally, if you remember, we have this final term here. So the final right-hand side term, which is NC plus 1, because we have NC right-hand side components in the right-hand side vector, an additional one, and an additional one for the Kelvin circulation boundary condition enforcement. That is simply equal to minus gamma of t minus delta t, which is given right here. All right, we can move on to the 7th step. And that is solving the system, which is identical to what we did in the steady case. Gamma, which is now equal to gamma 1 through gamma NV, which are all the bound vortices, and the gamma newly shed vortex. This entire vector is simply equal to a backslash RHS vector. The 8th step is calculating the air loads. Here, in contrast with the steady method, where we use the Kota-Joukowski theorem to calculate lift, we will use the unsteady Bernoulli equation to find lift. So, to find the lift, we require finding the differential in pressure across the camber line, or delta P across camber line. And for that, we use unsteady Bernoulli. And I'm going to be skipping the derivation of the lift equation based on unsteady Bernoulli. However, I will be probably posting another video to just solely to show the derivation. So just skipping the derivation, this is the final result, and I'll just write it down and I'll explain all the terms later. So going over each term, the delta Pj here is the differential in pressure on the camber line for panel J, or essentially across vortex J. So it is the the difference in pressure between the upper and lower surface for the jth panel or jth bound vector, bound vortex. Again, here this is the velocity induced by wake and kinematics And let me say, or make sure to say that this is in the wing fixed frame. So this bit of math is done in the wing fixed frame, and then later on we will transpose it or project it onto the inertial frame to find the lift force. This is the tangent unit vector. At each panel, or at panel J, or vortex, or bound vortex J. Again, this is the strength of that vortex, right? And I think we've gone over this before, so I don't need to redefine it. And this here is the length of panel. So the panel is defined to be the length of panel between two adjacent vortices. And then the second term here is the partial derivative in time of this term. And let me explain this term. This is, again, the gamma, or the vortex strength of kth vortex. And we were doing that because we are summing over J. So to give you an example, let's say we are trying to find the differential in pressure across the maybe fourth vortex, or fourth bound vortex. That means that this delta pj here, you find the velocity induced at that point, and then you dot product it with the unit vector the unit tangent vector at vortex j. You multiply that by the vortex strength and delta lj. And then for this term, the second term, since you are at the fourth vortex, you sum the vortex strength from the first bound vortex to the fourth bound vortex, and you take the partial derivative of that in time. So you essentially would have this term for the earlier time step and this term here for the time step, for the current time step, and you could use, for example, Euler's method to take the derivative of that expression in time. And the more time steps, or no, as J increases, so as you move along the wing, this term here will increase and you will sum more and more vortices. So let's say you are at the second bound vortex, then you sum from K1 to 2, so you say gamma 1 plus gamma 2. If you're at the fifth one, then it's gamma 1 plus gamma 2 plus gamma 3, so on and so forth. So I hope that sort of conveyed this point here. So after finding the delta Pj, we would like to find the lift. So lift is found by numerically integrating pressure difference and obtaining the vertical component in inertial frame, because we are interested in lift, and lift is defined as the vertical force in the inertial frame. Thus, we need to find the component of the force that we integrate for in the inertial frame. So to show an illustration, we have this diagram here, and we have, let's say this is some panel, right? And this is vortex J, right here, and we have found delta Pj, the differential in pressure, and by definition, pressure acts normal to the surface, and thus to find the force that is essentially the force that's the force vector resulting from this differential pressure, we take this differential in pressure and we multiply it by the length of the panel, which is delta Lj, and then to find the component of this force in the vertical axes here, all we do is we multiply this bit here by the inertial component of the vertical component of the normal unit vector at J in the inertial frame. Since we are interested in the inertial axes and not the wing fixed axes. So I'm going to put big X and big Z. All right, so to go over this again, this is differential in pressure across panel J or across bound vortex J. This is the length of the panel, and this here is the normal unit vector, or the component of the normal unit vector in the Z direction in the inertial frame at J. And then to find the total, well, let's say this is Lj, which is essentially the force component across panel J. To find the total lift, all we have to do is sum the force component we find here across the entire wing. So from 1 to the number of vortices we have. And can also find pitching moment similarly. So if you know where the force is at each panel and how much it is, you can calculate a moment about any arbitrary pitch axis you want. So here I'm going to do some manipulation. So, whoops. Let's insert delta Pj equation, which is the equation we found here, into lift equation and decompose into two parts. Let's do this right here. Doing this would result in the following equations, where L is equal to LA prime plus LB prime, and these are the two different components we're composing the force into, which correspond to this component and this component here. So let's define LA prime. That is equal to J equal to 1 through NV of rho UK plus U wake or UW and WK plus WW of dotted with the tangent vector in the wing fixed frame. So this is in wing fixed frame because we haven't done the transfer to the inertial frame yet. Multiplied by gamma j, and then here this is the x component in the inertial frame, the unit vector. sorry, not the x component, the z component of the unit vector in the inertial frame. So I'm just going to say inertial. Then we do a similar thing for LB. This is the second component corresponding to this bit. And that is j equal to 1 through NV rho delta L j partial derivative or time derivative of k equal to 1 through j gamma k and z j inertial. All right, so this is the equation for lift. So let me put a square around that and move this way to the left. Great, and then we can find the, I'm gonna give an example on how to find the pitching moment about the leading edge. But you can do something similar to any arbitrary pitching axis. MLE is equal to minus j equal to 1 through NV delta PJ delta LJ XJ, and this is wing fixed frame multiplied by the vertical component of the jth unit vector. All right, moving on to our last step. Step number 9 is the wake roll up. And in this step, we determine the motion of the wake or velocity. We update the wake position. And it is suggested that you do this in the inertial frame. All right, so there are two parts to doing this. Part A is for kth vortex, or shall I say kth wake vortex. Determine velocity induced at its position by I, the kinematics of the wing, no, sorry, not the kinematics of the wing. It's by the NV bound vortices, so by all the vortices that are bound to the wing, as well as the other vortices in the wake. So other vortices in the wake will affect the vortex in the wake in question. So each vortex affects the other, and it's sort of all coupled together. We don't really have to find the influence of the kinematics on the wake, because in the inertial frame of reference we're using, we are moving the wing. So this is how we get the displacement between the wing and the wake from the kinematics, is through moving the wing and not moving the wake. Also, let me put a note here to include the gamma of newly shed vortex. Since we have found the vortex strength of the newly shed vortex, you can include it when you find the velocities induced on the wake to propagate them in time. And then after finding the velocities, you get to part B, which is convecting the vortices in the wake. Convect wake vortices. And for that, we use Euler's method. Which essentially, for a general Euler's method, let's say we have some arbitrary quantity we want to propagate in time. That means dx dt is equal to x in the new time, or let's say n plus 1 minus xn over delta t. So this is a first order Euler. So an example of how to do that on the vortices is if we have our shed vortices here, so we want to find the x position of the shed vortices at the new time step, that is equal to their position, or sorry, let me put k instead, but you can put j just for illustration, plus the velocities, the velocity in the horizontal direction, u, that we found from part A in the inertial frame, multiplied by your time step delta t. And you do the same thing for the y coordinates, or in the y position, plus wk of delta t.